We're up to chapter 10 here. We're going to talk about energy in this chapter. Um, should be the last chapter for the first exam, I think. So when we talk about energy, which is sometimes part of what's referred to as thermodynamics, a lot of times we talk about kind of two parts to it when we're thinking about energy and really the flow of energy. One part is the system. And that's really the part of the universe that you're interested in the laboratory. That could be like your beaker, that could be like your test tube, whatever you're kind of doing the experiment in. And then pretty much everything outside of that is really what is sort of referred to as the surroundings. And a lot of times we look at it, say, in terms of energy, you know, the flow of it from perhaps the system to the surroundings or the surroundings back to the system. So it can flow again, it's sort of in both directions. When we talk about systems, there's three common types of systems that we come across. A lot of times we deal with open systems, and in an open system, you can have an exchange of mass and energy with the surroundings. In a closed system, we get the transfer of energy, but really not the mass. So nothing sort of goes in or out of, say, like the flask or beaker or whatever we may be dealing with. And lastly, sometimes we do look for like an isolated system where there's kind of no transfer of mass or energy. So there's some different types of systems depending on what you're dealing with and also what it will allow to, again, sort of flow from one place to the next. And here's some pictures of that here. We have our open system where obviously we could take in and out anything from that safe flask, and also we get the flow of heat. In a closed system, we put like a stopper on it. Obviously, nothing can escape at that point, but we still can, if kind of touch the outside, say, of the flask, the beaker, still be able to feel the flow of energy either in or out. And in an isolated system, it also, again, prevents any type of flow in and out of heat or energy, and also prevents, obviously, the flow of any type of mass out of that particular system. So energy is really the capacity to do work or to produce some type of change. And energy is work being done, which is the force times the distance. There's all kinds of sort of different types of energy that we sometimes deal with. For example, there's chemical energy that are stored within the structural units of chemical compounds. We have energy in terms of like bond either making or breaking. So, if we wanted to sort of make a bond in terms of energy, what typically happens when you want to make a bond is energy is released. So we get this release of energy. Again, everybody will slow down, and that's going to allow them to come together basically to make that bond. So usually when we make bonds, energy is released. That is, as we will talk about, we probably touched upon before, that again is what is known as being an exothermic type process when energy is released. When we want to break a bond, so if we have an actual bond formed and we want to break it, that is going to allow energy to be absorbed to do that. And that is an endothermic process. And again, the idea there is if you have a bond between two atoms and they gain energy, they're going to get enough energy to really kind of wiggle away from each other and break apart. There's also potential energy, and that's the energy, again, that is stored based on the position of an object. So again, that's, as I might have mentioned before, sort of like the classic giant boulder on top of a hill. It possesses a certain amount of potential energy based on its actual position. Kinetic energy, on the other hand, is the energy that is related to motion. So if this boulder did go over the hill, it would then become some kinetic energy occurring in that case. And the law of conservation of energy really sort of governs this. This is really what is sometimes referred to as the first law of thermodynamics, which is energy cannot be created nor destroyed. but it can be transformed from one version to the next. And that's sort of what we think about, at least in chemistry. In most cases, sort of this flow of energy is like a perfect flow of energy. So, what that means is if somebody sort of loses a certain amount of energy, somebody else will gain that amount of energy. So, if we have a system that loses, for example, 5 kilojoules of energy, we should have a surrounding that will gain those 5 kilojoules in energy, and vice versa. If the surroundings lost a certain amount of energy, then it's probably going to be the system that will pick up that amount of energy. So this sort of perfect exchange. And even the same idea here with our boulder, it possesses a certain amount of potential energy as it falls over kinetic energy. Once it hits the ground, it will transfer some of that energy to the ground. And again, if you sort of keep track of all the energy either gained or lost by somebody, again, it'll have that sort of perfect transfer of energy from one place to the next. And obviously, it will have a new potential energy, the boulder there, once it hits to the bottom there. Now, as I mentioned before, thermodynamics is really the study of heat and conversions of energy. It also, as you'll learn when you go to Chem 1B, is the study of whether or not, for example, a reaction will take place. So a lot of times we look at thermodynamics for the question of, under these conditions, would we expect this reaction to actually take place? In the case of the first law of thermodynamics, we deal a lot with, again, the energy component of it. And there are certain properties that are basically what are referred to as state functions. And state functions are properties basically are really not determined by how it got to a certain place, but it's really kind of only two important things, which is sort of where it started and where it ended. And that's what a lot of state functions are. It doesn't matter how you got there, it just matters really where you started and where you ended. Things like energy, pressure, volume, and temperature, these are all state functions. So, for example, if we look at the hikers, they started here, the bottom, the kind of blue hiker. The red hiker took the scenic route around the mountain. But in terms of potential energy here at the end, they're both basically the same. And the difference in their potential energy from where they started and where they ended, that we take kind of our final minus our initial for both of them, they will be the same. The sort of practical application of that in chemistry is sometimes people think that all chemical reactions, for example, happen in like a one-step sort of fashion. It's just like reactants, which is your starting material, goes to products. And that's not always the case. Sometimes reactions actually have any individual reactions where if you add them all together, you get kind of the overall thing happening. So, for example, what we could have in this case is A plus B, for example, makes C plus D, then C plus D will make E plus F. And if we add these guys together, anything that are opposite sides of the arrow that are exactly the same will actually cancel out. So that means C here will cancel and D will cancel since they're on opposite sides of the arrow and exactly the same. And everybody on the left-hand side stays there. So that's A plus B. Right-hand side stays there, E plus F. So it is possible that this reaction actually occurs in a kind of two-step process overall. But in the idea of energy, for example, it doesn't matter. There are state functions, which means it doesn't matter if it takes 2 steps, 1 step, like 40 steps to get there. In terms of the energy, it's really just about kind of where you start and where you end, which is really important. And that's what we see here, the change in energy, final minus initial, change in pressure, finals minus initial, volume, final minus initial, and temperature. They're all state functions, final minus initial. And again, if you just think about, for example, a change in temperature that maybe, you measured over, like a period of time, and maybe one took like a long time to get up to say 100 degrees. and the other you heated a lot faster and you're able to get it up to 100 degrees or really faster. It doesn't really matter how long it took it. The difference between the temperature is still like 100 and 0. For example, we started at 0. Any question out there? Now, when we talk about energy, there are certain units that are very common units that you should know, and I was talking about a couple of these here. The SI unit for energy is Newton meters, or a kilogram meter squared second squared. These are not negative, any of these, so they're just for PowerPoint, so it scratches them. 1 joule, as you can see there, a joule is a very common unit of energy, is equal to a kilogram meter squared second squared. That does pop up occasionally. I would say probably not too much in this class, but in like 1A and 1B, it does pop up a lot. And very common units is joules and kilojoules. So again, 1 kilojoule, which is 1,000 kilo, is 1,000 joules. So that's definitely something, these two things that you should know. Now, in addition to joules and kilojoules, which are very common units of energy, another really common unit of energy is calories. And these are lowercase kind of c for calories. And that's the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So the relationship between joules and calorie, which again is something that you do need to know, 4.184 joules. So 1 calorie, 4.184 joules. I say lowercase c because calories and kilocalories as well, by the way. A kilocalorie is 1,000 of the calories. That's also a very common sort of conversion as well. But I do say sort of lowercase c because there's also a capital C sort of calorie. And a capital C calorie is also sometimes referred to as a nutritional calorie. So one we kind of use for obviously food and nutrition and how many calories you're burning, say at the gym. One of the capital calories is actually 1,000 of the lowercase calories, which is also 1 kilocalorie. So again, there's also a nutritional calorie, like I said, which is basically 1,000 of the little calories. That's also why on some gym equipment you'll look at it and it'll tell you like how many kilocalories you burn rather than say nutritional calories. If you look at things like treadmills and stuff like that, they'll sometimes list it that way. So one way that we use energy is to change the temperature of a substance. Again, if we take something like ice and change it to liquid water, there's energy involved in that. Once again, if you had an ice cube, that would be your system. And obviously the surrounding air, right, would be, for example, your surroundings. And just a natural process is the ice cube will pick up the air and energy from the air and it will start to melt. That's because heat, for example, flows from hot to cold. So the flow of heat always goes from hot to cold. And that's why when you take out an ice cube from the freezer and just put it on the bench or whatever, or the table, the air outside is hotter than the ice cube's temperature. So the heat from the air outside will flow into the ice cube. And that's what's supplying the heat that's causing it to melt. That's also what has happened again when you take liquid water and you throw it back into the freezer. Again, the liquid water is probably like room temperature water, which at that point is hotter than the air inside the freezer. So all the heat and energy from the liquid water will flow out of the liquid water, and that's going to cause it to, again, freeze and become ice in that particular case. And you get ice cubes in that case. In that situation, again, the ice or the water would be your system and the surroundings would be the air in the freezer. And in that case, it's actually the surroundings picking up all the energy from the water in that case. Any questions on that there? Now, thermal energy is associated with the random motion of molecules. And the more molecules or atoms that you have in a sample, the hotter the sample will get, and you'll have a greater amount of thermal energy associated with it. Now, thermal energy, again, is associated with the amount of particles or atoms that are present. It is different than temperature. Temperature is something that we use to basically measure the amount of energy change that's occurring, for example, within a substance. So, for example, if you had a cup of coffee at 70 degrees Celsius and a bathtub at 40 degrees Celsius, the bathtub would actually have more thermal energy than the cup of coffee, even though the cup of coffee is hotter in terms of its temperature. Therefore, more water molecules and more molecular motion. Again, if you just think about sort of the volume of the difference, right? A lot more molecules in here moving around, a lot more thermal energy. There's actually less molecules in there, so it has less thermal energy. The reason the temperature is higher is the amount of, say, water in there is much less than a bathtub, right? So if you think about if you had a very small amount of water and you heated it up, right, it's going to heat up a lot faster than if you had a giant, like, pot of water, right? It's going to take a lot longer for that to get warm, just because of the pure volume of it there. So that's why, again, we could have like a cup of coffee that has a higher temperature because that volume of water will not take as long, for example, to heat up, and you could actually get it to a higher temperature than if you apply sort of the same heat to your bathtub water. Again, with that amount of water, it's going to take a little bit longer to reach the same temperature because there's a greater amount of volume of water molecules present. Any questions on that there? Now, as I mentioned before, heat is a flow of energy due to a temperature difference, and that is a transfer of thermal energy between two bodies that are at different temperatures. Once again, we're going to have that flow from the higher to the colder temperature. Again, the warmer object will start to cool down. The colder object will gain the energy and start to increase its temperature. And as we touched upon a number of times here, once again, officially here, exothermic processes are any processes that basically will give off energy or release heat or energy. And for example, if you lit a match, if you put your hand next to it, you obviously can feel the heat coming off of it. Kind of same idea, obviously, when you light your Bunsen burner, you can feel the heat coming off, obviously, of the flame to the surroundings. An endothermic process, again, is any process which basically absorbs energy. And when we talk about energy, uh, the way we represent, for example, things that are exothermic or things that are endothermic in terms of their process is a lot of times the values are going to be perhaps the same if you're doing some type of process where we're following the flow of energy from one object to the next. But it's actually the sign that tells us whether or not we're sort of dealing with an exothermic or endothermic type process. And that what I'm talking about is the sign of the value of energy for that process. Now, there's really kind of two ways that we look at energy or heat in calculations a lot of times in chemistry, and that is a lot of times we will calculate Q, which is heat, or delta H, which is the change in enthalpy. And the change in enthalpy is the most common way that we oftentimes look at sort of the energy associated with a particular reaction. The delta H of a reaction is basically the energy change that occurs in that reaction. And typically speaking, if you have an exothermic type of situation happening and you go to calculate Q or delta H, you will end up with a negative value. And that negative sign is important because it does indicate to people that you are dealing with a exothermic type process and overall heat and energy is being released. On the other hand, an endothermic process, uh, our delta H, which again, same thing as above, typically will have a positive value. So it's really important, for example, when you do some energy type calculations, either again, the energy or the heat sort of calculation, that if you do get a negative number, it's important to leave the negative number because, again, it tells people that you're dealing with something that's an exothermic type process. And clearly, if you get a positive number, then obviously you would leave it positive, and that also tells people that it's an endothermic reaction. Now, I would say in most cases, when we look at a reaction, which again, when we look at an equation, we have our reactants, which is our starting material. And they go to products on the other side of the arrow, and that is what is made as a result of it. A lot of times in chemistry, the way that you are sort of given this information is you'll be given the equation, and at the end of the equation, a lot of times they'll give you the delta H value, and it will be either positive or negative. And again, depending on which sign that they give you, the number really doesn't matter all that much in determination of exothermic or endothermic. It's really just the sign, whether it's positive or a negative number. And again, you can use that to determine overall what is happening. So I would say in chemistry, that's a super common way that energy is displayed in an equation. They oftentimes, again, give you the equation at the end. They just kind of tell you the delta H for this reaction is either this number or that number, and either it's positive or negative. Any questions on up there? So these are what are referred to sometimes as energy diagrams. And these energy diagrams are displaying basically two types of reactions that we just talked about, exothermic or endothermic reactions. And again, as we just mentioned there, we take our reactants to our products in a reaction. So when we look at the one here on the left, this is where our reactants are starting. And this is the energy of the products when the whole reaction is all said and done. And we can see in this particular case that the energy of our reactants are higher than our products. So the only way to get down in terms of energy is overall energy is released in this case, right? That allows the energy of the reactants to come down to the energy of the products. And that is definitely always an exothermic reaction. So if you see any of these sort of energy diagrams and you see the reactants higher in energy than the products, that should always mean that you're looking at an exothermic reaction. The opposite is what we see actually over here. That is our reactants down here, and that is our products up here. So in this case, the reactants are lower in energy than our products. So the only way to sort of get there is energy has to be absorbed to sort of get up higher in energy rather than over here, reactants are greater in energy than our products. So what happens when we have a reaction that actually takes place? Well, the only thing that happens in a chemical reaction is we break bonds. So we break all the bonds on the reactant side. So all these bonds over here gets broken, and we make all these bonds basically on the product side. That's no change in the nucleus, no change in protons or neutrons. That is why, as you're probably familiar with, or will be when we get to that chapter, that's why we balance equations. So if we start with like 4 carbons, we end with 4 carbons, because the only thing that happens in a chemical reaction is basically bonds being made and broken, and bonds are all about electrons basically. So it's really only electrons sort of involved in the process of a reaction taking place. And two things has to sort of happen for products to actually take place. One thing is they have to sort of collide with each other. So the two things that are reacting actually has to make contact and hit each other. They actually do have to hit each other in the right location. So there's sort of like an active spot, if you will, on both of them. They actually do need to collide in that correct sort of location for a reaction to take place. And they also need to, in addition to sort of colliding, they need the right amount of energy, which is the minimum amount of energy required for a reaction to take place. And that means that if either one of those things really do not happen, they don't really hit each other in the right spot, or they don't hit each other with the right amount of energy, you actually will not get any products formed in that case. So not all collisions where things bump into each other will actually form products. Again, there's these two sort of things that has to be met in order for a reaction to take place. Now, when we talk about the amount of energy, that is actually the hill that the reactants has to climb to get to the other side. That is what is known as the activation energy, which is E of A. The activation energy is the energy hill that those reactants has to climb basically to get to the other side. And for our exothermic reactions there on the left, this is our hill here for our endothermic reaction. And that is our activation energy hill, E of A. And you could see as well a couple of things, probably just logically thinking about it. That hill that they have to climb to get to the other side is really important in terms, for example, of how fast or slow a reaction would take place, right? So if you have a much bigger hill to climb, there's going to be less reactants that have enough energy basically to climb and get to the other side. If you have a much smaller hill to climb to get to the other side, there's probably going to be a greater amount of reactants that could actually make it up and over that hill. So what happens as they kind of go up the hill here, as they sort of progress up this particular hill, you start to get bonds being broken. And at the same time, you have bonds being made. So you actually have sort of partially broken bonds happening, and then you have partially made bonds. Being made. Until you get to the very, very top here of the hill. And the very top of the hill is what is sometimes referred to as a transition state. And at the very, very top of the hill, you oftentimes will have a product which is known as a transition state complex or an activated complex. And when we think about energy, just in general in chemistry, if we have high energy, say, versus low energy, which one do you think would be more stable situation, high energy or low energy? Most stable situation for things is going to be low energy. Yeah. So things want to be in low energy like we do, right? We don't want to be high energy all the time, right? We want to relax, kick it back, and all that good stuff. And that's what happens in chemistry. Pretty much a lot of things that happen in chemistry, the overall reason a lot of times is to get to a much better state in terms of energy, a much lower, more stable state in terms of energy. So when you get to this transition state in a reaction, which is the top of the hill in terms of energy, you actually have this thing here, which is super unstable. And usually what happens is it will very quickly drop to the other side. Obviously, this is our transition state here. And again, this guy would drop to the other side really, really quickly. Usually those guys, those transition state complexes, they're again things that have partially made bonds, partially broken bonds, which is why they're really high in energy and very, very unstable. And they don't hang around a long time because they're really in a state of like moving to the next thing. So they're kind of that, again, that transition state, which is why it's referred to as a transition state complex. Any questions on that there? Now we talked about delta H, which is our change in enthalpy, which is again a very common way that we look at a reaction and sort of think about energy. And one way, as we'll talk about here, that you could calculate the delta H of the reaction is to take the delta H of our products minus the delta H of your reactant. So basically, again, your final minus your initial. If you think about a chemical reaction, your products is your final state, right? And your reactants is your initial state, right? And that's why a lot of things that we calculate in chemistry, we take like the difference in terms of the products minus the reactants, because again, that's sort of like your final state minus your initial state. So the difference here between the energy of the reactants and the energy of the products here, if that was a straight line drawn, is actually the delta H of this reaction. And if we think about just mathematically for the exothermic situation, the energy of our products is a smaller number than the energy of our reactants. It's much higher. It's a larger number. So whenever we take a small number minus a larger number, we will get, again, our delta H is going to result in a negative value. Now, if you look over here for our endothermic, our reactants and our products are here. So this change in energy is the change in enthalpy here. And in this situation, though, our products are actually higher in energy, which means it's going to be a larger number minus a smaller number. And when you do that, you will end up with a positive value for delta H. So that is why, again, when you see a change in enthalpy or delta H value for a particular reaction and it's positive or negative, it is going to basically tell you if it's exothermic or endothermic. Any questions on any of that there? And again, here's just another sort of version of an energy diagram. These are our reactants going to our products. So once again, our reactants are higher in energy than our products. Again, heat and energy has to be given off in that situation, and that would be an exothermic reaction. Here, it's actually our reactants down here, lower in energy than our products. So again, heat and energy has to be absorbed in this situation. And again, that's going to result in an endothermic type process that's going on. So it's just sort of another version of an energy sort of diagram there. Again, here on the left, that will give us a delta H is going to be negative. And here on the right, that will give us a delta H value that will be positive to represent either that exothermic or endothermic type process. Now, a couple of other things when we look at chemical equations and reactions and think about exothermic and endothermic. So as we talked about, our reactants go to products in a chemical reaction. When we think of energy in an exothermic reaction, we think of the heat as being a product. So sometimes, and again, I would say not too much in this particular class, will you actually see the energy written into the equation, but sometimes you might. But if it is written into the equation, it would be on the product side, like it's being given off or released in that situation. And that is opposite for our endothermic. If it was written into an equation, it would be written in as a reactant or on a reactant side, like it's being absorbed or being added to our reactants in this reaction. So that is also a very common way, and it can just be a generic, they write heat on one side of the arrow versus heat written on the other side of the arrow. Here again, kilocalories is a common unit of energy, and they actually gave us a value in this particular case. So when we have an exothermic process, heat is released, product side of the equation, endothermic heat is absorbed, reactant side. Now, when we talk about sort of this conservation of energy and this flow of energy and the relationship between our system and say our surroundings, if our system released, say 50 kilojoules of energy, in terms of the system, it would be a negative value as it is being released in exothermic. In terms of our surroundings, When it picks up that 50 kilojoules of energy, it will actually be a positive value for our surroundings. The number of the energy that's being sort of released or absorbed in, say, a chemical reaction will be the same. So the physical number or value that you get will be the same value. In this example here, they're both 50. So again, this is why the negative or the positive being written into the answer is important, because again, with the negative 50, we understand that for our system in this situation is going to be exothermic, but the positive, say 50, and again, we typically wouldn't write the positive part of it. We just obviously just write 50, would indicate that it's being absorbed. So the amount of energy going one way or the other is usually the same value, but the sign is really the only thing that changes to indicate whether or not it is exothermic or endothermic. Any questions on that there? So here's an example of that in this isolated, insulated container. We have hot water and cold water. Once again, energy is going to transfer from the left-hand side to the right-hand side as it is obviously hotter in terms of its temperature. And what we see is a lot more energy happening over here, which is going to, again, cross over to the other side. That's going to allow this side on the right to gain more energy and start moving a little faster. The result of that is, in terms of temperature, we'll start to see an increase in the temperature of the colder water, and we'll start to see a decrease in the temperature of the hotter water as it's releasing a lot of its energy. As the hot water releases its energy, it's going to kind of slow down and not have as much movement. And obviously, we're going to see that in terms of temperature. And eventually, they'll hit about halfway between both temperatures. So if you take 90 and 10, it got 100 divided by 2, you'll end up somewhere there in 50. As they come to equilibrium, basically, and both sides basically will have the same temperature. So temperature is a way that we can really assess, for example, is this process we're looking at endothermic or exothermic, right? So in terms of temperature, we could follow the temperature. And if our final temperature is smaller than our initial temperature, right? Our initial temperature was larger and our final temperature was smaller, would that be a endothermic or exothermic process? What do you think? It would be a exothermic process, right? We had a much larger temperature. The only way for the temperature to drop is it has to give off that energy. It's going to slow down, and the result of that is the temperature is going to decrease. So this would result in a exothermic process. And then obviously the opposite would be true if our final temperature ended up being larger than our initial temperature. Then we are looking at something that is endothermic. So for example, a pretty simple thing that we'll talk a lot about here is if you have, say, just some water at room temperature and you dropped an object that was really hot into it. When you do so, that hot object is going to release all that energy to the water, and we will see the initial temperature of the water, wherever it started, the temperature of the water will start to rise, right? The temperature of the metal in that case would also start to decrease, right? From wherever it started, say it started at 100, and now it will start dropping down. By the way, if I did that example and threw something hot into, say, water that was at a colder temperature than, say, that object, what will be the final temperature of the hot object I put in the water? It will end up being the exact same temperature as the water ended up being, right? They'll end up being at the exact same temperature. They'll equilibrate to the same temperature. So that's a really common, easy way you can figure out the, say, final temperature of an object. You could just follow the change in temperature of the water, and whatever the water ends up being, because it's sitting in there, is basically going to equilibrate to the same temperature at that point. Questions on that there? So we talked about enthalpy there, so let's officially kind of talk a little bit about enthalpy. So as I mentioned before, probably the most common way that energy is related to in chemistry is enthalpy. And enthalpy, which is abbreviated with an H, is the heat either released or absorbed during a chemical process. A lot of times we calculate, again, the change in enthalpy, which is the difference between basically the product and the reactants. Once again, as I mentioned before, that's basically our final state minus our initial state in this particular case. And again, whether or not the delta H is positive or negative, and again, the number really doesn't matter in that sort of determination, will basically be what will determine if it's going to be exothermic or endothermic. So basically, when we do a change in enthalpy calculation, we add up all the enthalpy values for our products, and we subtract it from all the enthalpy values from our reactants. So one way that you could do this, for example, is if you had, say, a reaction like this, you could go to an actual delta H of formation, and this is actually like a table. And in this table, you could look up values for the delta H for, say, A, B, and C, and I'll just make it up, obviously, 10 kilojoules per mole. We'll go with minus 5 kilojoules per mole. And actually, no, we'll do 15. And then we could just do like 25 kilojoules per mole. So a lot of times you could look up these values in the table. And when you do that, you want to make sure a couple of things. You want to make sure, obviously, you find the right thing you're looking for, but you also want to make sure you find it in the correct state. So if it's a solid versus a liquid versus something that's aqueous, you want to make sure that when you look it up, you actually do find it. So to calculate, for example, the delta H of this reaction, we would simply take the delta H of all of our products, we would add them together, and minus the delta H of all of our reactants. And again, just subtract the two. Now, we do have to actually take into account the coefficients when we do this. So you do have to multiply the values that you find in the table by any coefficients that are in the equation. Those are sometimes referred to as the moles of each of those things. So in this case, our delta H of our reaction here would be 3, because that is the coefficient, times the value of C, which was 25 kilojoules per mole. We would then subtract it from all of our product sides. So on our product side, we have A. Once again, we would have to take 2 times the value of A in the table, which would be 10 kilojoules. We're going to add it to B. In this case, the coefficient is 1, which means you really don't need to put the 1, but I'll put it here if you want. And that'll be negative 15 kilojoules per mole. And that's our reactant side. And if we do that here, in my made up example, we will end up with 3 times 25 minus 2 times 10 plus minus 15, going to get us a 70, it looks like, perhaps in this case. And that is going to get us here 70 kilojoules. Let's make sure 2 times 10 plus. Yeah. Now, based on this made up one, is this reaction endothermic or exothermic? My delta H value is positive or negative? Positive, right? So because this is positive, this would be an endothermic reaction. Any questions on that there? All right, so let's take a look here. Why don't you try one here? Again, here's the values you can find in that table. Calculate the delta H for this reaction, and is it exothermic or endothermic? Okay, so let's take a look. Again, we're going to calculate basically our delta H of our reaction. Again, all the delta H of our products is minus the delta H of our reactants. So on the product side, which is this side, we're going to take Again, the coefficient, which is 2, so 2 times the value that we see in that table for NaOH. We're going to add it to our value for H2, which happens to be 0 in this case. So that is all of our products. We're going to subtract it from all of our reactants. Again, we're going to take the coefficient into account, which is 2 times 0 for that. And we're going to add it to our coefficient there, which is 2 times the value of water. And this would be all of our reactants in this case. So we'll end up here with, looks like, minus 368 kilojoules. There's any question on the calculation there. Reaction endothermic, exothermic. It is exothermic, right? And again, it is the negative that tells us that in this particular case. Any questions on that there? Yeah. So when you look at an equation, reactants are always on the left-hand side of the arrow. Products are always on the right-hand side of the arrow. Yeah. Other questions? And again, remember, we're kind of bouncing around, so they kind of assume that you did those earlier chapters. So, that's why some of the things here might look new. Other questions? All right. Let's maybe try one more. Try this one, I think. All right, try this one here. Okay, so once again, let's take a look here. Delta H of this reaction going to be, again, our delta H of our products minus the delta H of our reactants. So we'll start on the product side there. So we do have a 12, so we do need to take 12 times the CO2 value, which is minus 393.5 kilojoules. We're going to add it to our 6 waters there. So 6 times the value of water minus 286 kilojoules. That's going to take care, once again, of all of our products. We'll subtract it. I'll just go underneath there from our reactants. We have a 2 there for that guy, which is 4904. And we're going to add it to 15 times the value of O2, which is 0 in this case. And that's going to get us here 12 times minus 393.5 plus 6 times minus 286 minus 2 times 4904. That's going to get us something like minus 6536 kilojoules. Once again, we see a negative, which tells us it is exothermic. Any questions on how to calculate delta H for a reaction? Okay. All right. So again, that is a very common sort of energy type of value. But more commonly in this class, we do calculate what is sometimes referred to as the specific heat capacity. And once again, this is not a negative here or there. And the specific heat capacity is the amount of energy that's required to change the temperature of 1 gram of a substance by 1 degree Celsius. There's actually a specific heat equation. Q is equal to ms delta T. Q is heat or energy. It typically will have units of joules or little calories. M is mass, which will typically have units of grams. S is the specific heat capacity. And it will have units of joules per gram per degree Celsius or calories per gram per degree Celsius. And change in temperature is going to always be final minus initial. This is probably one of the few things in chemistry where degrees Celsius, not Kelvin, is used. So we typically will use degrees Celsius here for our change in temperature. Now, M is going to be a positive number. S is the specific heat capacity, which is also a positive number. And that means that the only way that you can get a negative Q is the temperature value. And that's why you always want to do final minus initial, not what a lot of people commonly do, which is just take the difference of the temperatures. So that final minus initial is really important because that's what's going to determine whether or not you will end up with a positive or negative Q. And as I mentioned before, if Q is positive, it will be an endothermic, again, endothermic process. And if Q is negative, it will be a exothermic process. You could calculate Q, and it is the same as the delta H at constant pressure, so you could actually calculate the heat and energy. Two really important numbers that you definitely need to know are these, and that's the specific heat of water, actually liquid water, by the way. And that is specific heat of liquid water is 4.184 joules per gram per degree Celsius. Or bless you, sometimes people use 1 calorie per gram per degree Celsius for the specific heat of water. Those numbers should look familiar to you, as those are the numbers that we used to convert between joules and calories, basically. So there's 4.184 joules in a calorie, and that's also really the specific heat capacity of liquid water. That is a value you use a lot when you're doing these calculations, and it's like never given to you. Yeah. So it's just like something they assume that you know, and even in problems, it's assumed that you know those values and you just use it. Now, if I have a specific heat capacity, which has units of joules per gram per degree Celsius, if I have a large specific heat capacity versus a small specific heat capacity, the large specific heat capacity will take more or less energy to change the temperature of that substance by 1 degree Celsius. If you have a large value of specific heat capacity, it will be, what do you think? Will it take more or less energy to change the temperature? It would take more, right? The only way you can get a large number mathematically is this number needs to be high on top, right? Large on top, small on the bottom gives you a large value, right? If you have a really small specific heat capacity, it doesn't take a lot of energy basically to change the temperature of that substance. By the way, water has a very high specific heat capacity, which is why if you go back to our example of the bathtub versus coffee cup, that amount of water is going to take a lot of energy, right, to change that temperature. You have a lot less mass of it. In that case, it's going to take a lot less energy to change it and get a higher temperature change. So there is specific heat capacity of liquid water. You can see ice, which is the solid version, is 2.03, and water is 2 when it's in the gas state. So this also brings up a really good idea that, you do need to want to make sure you grab it in the correct state. You're not just grabbing it in the wrong state, especially water. I would say most of the time water is going to be liquid, but it may not always be. So if you're doing with something ice or steam, you got to use obviously the proper specific heat capacity. Again, water, as you can see, has a very high specific heat capacity. That is also why people freak out when the ocean water, right, changes by just a very small amount of temperature. Because think about how much water is in there and how much energy is needed just to move it like a tick on the temperature scale. It takes a lot of energy to do that. All right, so why don't you try one here? Determine the amount of energy as heat that's required to raise the temperature of 10-gram sample of aluminum from 0.89 joules per gram per degree Celsius from 25 degrees to 58. What is the answer in both joules and calories? Get this one here. So obviously we're going to use our specific heat equation. Q is equal to ms delta T. By the way, for specific heat capacity, sometimes people will use C for the symbol, and sometimes people will use like SH. They're all basically the same sort of thing, basically specific heat capacity. In this case, we do have our mass, which is 10 grams. We do have the specific heat capacity of 0.89 joules per gram per degree Celsius given to us. And we do have our initial temperature of 25 degrees Celsius and our final temperature of 58 degrees Celsius. So we really have everything we need just to plug and chug into here. So 10 grams. We'll go our specific heat capacity here, joules per gram per degree Celsius. By the way, the one with the 3 units is the specific heat capacity. It is not Q, and sometimes people always get those guys kind of backwards. Q will only have 1 unit. It will either be joules or it will be calories. So the specific heat capacity will always have 3 units. So don't get those guys kind of backwards. Once again, remember, we do want to go final minus initial here. So in this case, it's going to be 58 minus 25 degrees Celsius. And if we do that there, we will end up with 293.7 unit-wise grams canceled, degrees Celsius cancels. We will end up with joules. Significant figure-wise, we got 3 there, right? We got 2 there. When we subtract our temperature, we go to the whole number, which is 33, which is 2, which means we really should end up here at 290, right? In terms of our significant figures. Any questions on that there? That obviously is our joules. It also wants calories. So remember that there are 4.184 joules in 1 calorie. So we'll go joules on the bottom here and 1 calorie up on top. The joules there will cancel. We'll end up with, if you use the rounded number here, yeah, we'll call it 69 calories in this case. If you use the sort of non-rounded number at that point, you'll end up with like 70, I think. Yeah. So, any questions on that? Again, here I probably used a rounded number since that was one of the answers and just kind of do the conversion with that one. Any questions? This is a endothermic process, right? We have Q that is positive. So this is a positive Q, which is endothermic. And we see that because our temperature actually increased, right? So as this thing was gaining energy and absorbing that energy, the result of that is we see the temperature start to rise, which tells us that it is an endothermic process. Question on that one there. All right, we will lay it up there, I think, for today.